the program. The next speaker is Piotr Bizon from Jagiellonian University and the Einstein Institute, and he will tell us about globally regular instability of ADS3.
Thank you very much. Thank you for the invitation to speak here. Can you hear me? So this is a joint work with Joanna Jałmużna on anti-de Sitter spacetimes in 2+1 dimensions. Here's the outline of my talk. I will first review very briefly the conjectured instability of ADS, which Gustav mentioned, in dimensions 4 and higher. In this talk, little d will be the number of special dimensions. So the spacetime is d+1 dimensional. So I will briefly review this result on instability in these higher dimensions, 4 and higher. Then I will try to explain you why the case of 2+1 dimensions is different. And then I will introduce a certain method, which is called analyticity street method, which is a method of detecting singularities for nonlinear evolution equations, not only wave equations, which is relatively which is very well known in other areas of applied mathematics, in particular fluid dynamics, but not so well known in relativity. At least I learned about this method pretty recently. And then I will show you how to apply this method to get evidence that in fact for small perturbations of ADS3, solutions remain globally regular for all times. However, they behave in a turbulent manner, so there is instability without black hole formation. And if I have time, I mention some open questions. So, so you all know what is anti-de Sitter spacetime. I will be using globally regular coordinates x, t, and angular variables, which live on d-1 dimensional sphere. And this particular form of the metric is very convenient because from this we immediately see the causal structure of ADS. We see that the ADS metric is conformal to the metric of the Einstein universe, but it covers only half of the Einstein universe because the variable x runs from 0 to pi half, rather from 0 to pi, which would cover the whole d-1 dimensional sphere. And the time is unwrapped. Here is the conformal diagram with all angular variables suppressed of ADS, which looks the same in any dimension. And the most important feature, at least from the point of view of studying waves on this spacetime, is the fact that it has that the null and special infinity is time-like, and any null geodesic sent from the center or from any point in the bulk reaches the boundary in finite time. So this means that ADS is not globally hyperbolic, and to define dynamics in such a situation, we need to prescribe boundary conditions at conformal infinity. And for example, if we study Maxwell equations, we must tell the photon what to do once it reaches the boundary. It can leave the spacetime or it can reflect back. And if it reflects, it can change polarization, for example. So this has to be prescribed in order to have a well-defined evolution. well, this is just pure ADS, but asymptotically ADS spacetime, well, at least in this setting which I'm interested in, are just defined as spacetimes which share the same conformal boundary. They have the same conformal boundary as ADS, so all these problems with non-globally hyperbolic behavior well, are present in asymptotic ADS spacetime as well. So now there is a question: is this solution stable? We've seen conjecture 2 in Gustav's talk, and well, naively one might think that this solution should be stable because this is a ground state by positive energy theorem, similarly to Minkowski, which is a ground state for asymptotically flat spacetime. But there is a key difference between Minkowski and ADS. And I should emphasize that the fact that the solution, well, in this case an equilibrium solution, is a ground state by no means implies that this solution is stable in the sense that small perturbations remain small for all times. This need not be the case. And then the key difference between Minkowski and ADS is that the stability, the nonlinear stability of Minkowski is due to so-called dissipation by dispersion. So the energy of small perturbation escapes to infinity and never comes back. While in the case of ADS, waves which would like to escape to infinity will bounce back at the conformal boundary, which acts like a mirror, at least for reflecting boundary conditions. So actually this was a good point which Gustav made. So and in this talk I will be restricting myself to these reflecting boundary conditions or no flux boundary conditions. So because only then the energy in this case is conserved. For outgoing conditions which can be imposed, but not for all fields, but for some can, like Maxwell, for example, the situation might be entirely different. So because these waves bounce back and return to the bulk, this leads to some very complicated phenomenology of wave interactions, which one has to understand to make statements about stability. So this is a hard problem, and so it's natural to make a first step under some simplifying assumption, and this assumption is spherical symmetry. Now in spherical symmetry there is Birkhoff's theorem. So in vacuum or for electrovacuum, so we need to add matter to generate dynamics, and there is no dynamical degrees of freedom in spherically symmetric gravitational field. And the simplest choice is a massless scalar field. So here, well, one could add a mass to this field, but I'm again restricting myself to the massless case. And then we have Einstein equations with a negative lambda coupled. This is a stress energy tensor for the scalar field, which satisfies the wave equation on this dynamical background. So this is so within this model, we have been studying the issue of stability of ADS, and these studies are more conveniently done in these coordinates, the same global coordinates as for pure ADS, but now we have two functions, metric functions, A and delta, which depend on T and X. This is spherical symmetry, and these functions satisfy Einstein equations coupled to the scalar field. It's convenient to define, rather than using the A function, to use the mass function M, which is like a mass aspect function, which depends on the dimension. And then using some units like mpg equal d minus 1, this is a convenient choice, and using primes as special derivatives and dots as time derivatives, we arrive at this system of equations. So this is the first equation is the quasi-linear wave equation for the for the scalar field on this dynamical background, and it is coupled to two ordinary differential equations for the metric functions m or a and delta. Now, as I said, to make sense of dynamics, we need to impose boundary conditions, and in the case of massless field, as long as we assume that solutions are smooth, so initial data are smooth, then we have no choice. The smoothness condition determines boundary conditions together with conditions that the mass is finite. And this is the behavior of the fields near the conformal boundary, which is at pi half. And under these boundary conditions, it is known, well, that this system of equations is well posed. This was actually shown for d equals 3, but I guess the generalization to other dimensions is straightforward. So what we are interested in is understanding evolution of small perturbation of ADS. ADS is an explicit solution of this system, which is just zero. So we want to understand the perturbation of these zero solutions, small perturbations of these zero solutions, how they evolve for long times, for smooth perturbations. And studying this problem numerically, we arrived at this conjecture. We did it in 4 space-time dimensions for d equals 3. So we found that there is a very large class of arbitrarily small perturbations under which ADS4 is unstable. And the evidence for this conjecture is based on several pieces. So one is a perturbative argument which is based on the character of the linearized spectrum around ADS. This spectrum is so-called fully resonant, which means that the waves are non-dispersive. They have long time to interact, so waves which travel nearby. And the interaction between these waves leads to resonances which generate higher and higher harmonics. And if you do naive perturbation, nonlinear perturbation analysis, you get, because of these resonances, you get secular terms which predict the breakdown of the perturbation analysis. And as a result of generating these higher harmonics, the energy spectrum is shifted to higher energies. So this is reminiscent of turbulence behavior in fluids. And actually the same argument was given for vacuum Einstein equations. Now, on a heuristic level, it is natural to expect that because of this transfer of energy to higher frequencies, and which means that energy gets concentrated on smaller and smaller scales, eventually by this concentration of energy, a horizon will be formed. And this perturbative and heuristic argument were supported by nonlinear simulations of this system, which I showed you on a previous slide. And in agreement with this perturbative argument, after time which scales like 1 over epsilon squared, this is exactly the time at which the perturbation analysis breaks down, perturbations start growing, actually growing exponentially. And if you continue the evolution, now it's a fully nonlinear evolution, you get a black hole. This scaling is very important because you cannot numerically go to arbitrarily small data, so you need to have some kind of scaling which allows you to extrapolate your results to arbitrarily small data. And so this scaling was very important. And this was independently verified by these people who also extended these results. Now, was in 3+1 dimensions, but generalization to higher dimension is straightforward. It's qualitatively exactly the same thing. Of course, there are quantitative differences. And this is due to the fact that starting from d equals 3, Einstein equations are supercritical. So this is all I wanted to say about higher dimensional case, because I am assuming that in one way or another you heard about this. So now I'm coming to the subject of my talk, which is ADS gravity in two special dimensions. Now, as I will show in a few slides, the spectral properties of linearized operator around ADS is not very different in 2 dimensions than in higher dimensions. And therefore, also a nonlinear perturbation analysis, well, this first argument for instability of ADS, which I showed you a moment ago, remains valid. However, so this is the same in 2 dimensions, but what is different is, is the criticality of the model. So maybe I should say that in PDE theory there is one can classify nonlinear wave equation or more general nonlinear evolution equations into different classes depending on how energy scales as you rescale space and time. And this is a very important heuristic tool in predicting, to making predictions about singularity formation. And we see it here. So this is a combination. This is Newton's constant time mass and some length scale, 2 power d minus 1. This combination is dimensionless. And this is exactly the combination which appears in a Schwarzschild solution in d dimensions, right? So for example, when d is 3, this is gm over L. Now in d equal 2, this just goes away. So in d equal 2, the Newton's constant has a dimension of mass inverse. And the concentration of energy is irrelevant. So this heuristic argument I gave you before, the turbulent transfer should lead to black hole formation, is not valid here, because what matters is the total mass, not its concentration in 2 dimensions. And another way of saying is that d equal 2 is the critical dimension of Einstein for Einstein equations, while d equals 3 is the lowest supercritical dimensions. And this is very nicely reflected in an explicit family of ADS Schwarzschild solutions, which in 2 dimensions, so if I now I decompactify the variable x I had before to write it in a more familiar form. So this is ADS Schwarzschild family in 2 dimensions, when n is 1 minus m plus r squared over L squared. This is the ADS range. And depending on the value of m, we have three cases. So when m is 0, this is just ADS in 2+1 dimensions. When m is between 0 and 1, then because this function is not equal to 1 at the origin, we have a conical singularity at the origin. This was first found by Staruszkiewicz 50 years ago. And this corresponds to just a point mass sitting at the center. So there is a Dirac delta mass at the center. And when m is bigger than 1, we have BTZ black holes, so which are very similar to Schwarzschild ADS black holes in higher dimensions. Now, from this, you see immediately, since ADS has mass 0 and mass is conserved, if we take a small perturbation which has mass slightly above 0, then this solution cannot evolve into a BTZ black hole because it just does not have enough energy. So there is a question: what happens? There is no natural candidate for the end state. Well, I should mention that the numerical studies of this model has been pioneered by Franz Pretorius and Matt Choptuik 13 years ago, but they were not concerned with small perturbations of ADS. They were interested rather in this transition between, in the region when m is near 1. I'll come to this later. Okay. So what are the possibilities? So we know that this BTZ black hole cannot be formed. We know this a priori. So I wrote here the system of equations which I showed you before in the general number of dimensions. Now I show it in d equal 2. And in this case, it's convenient to, rather than using this a and delta, to use this function beta, which is a combination of these two. And this system of equations looks like this. Now, the previous argument showed that for small perturbations, evolution cannot go to BTZ black hole. But actually, a stronger statement is true. The black hole cannot be formed if mass is below 1. So the total mass is just the limit of this function m, the mass function, at the conformal boundary. And if this is less than 1, the apparent horizon cannot form, because the condition for the apparent horizon is that this quantity is 0 and r is the radial coordinate, and this is just equal to the function a, and the function a is related to the mass by this formula. So when m is less than, well, and m, as you see from here, is a monotone function. It goes from 0 to some value which is less than 1. So if this is a monotone function which is below 1, this is always positive. So the black hole formation is excluded a priori. So we are left with a dichotomy. Either the solution remains regular for all times, or it forms a naked singularity. And now I will try to give you evidence that the first possibility is realized. So I will try to exclude this. And for this I will use this method, analyticity strip method, which is quite old, but not so well known in this community. So let me go through, explain this method now. I will spend 2 slides explaining this method. So suppose we have, so this is a method which attempts to give answer towards the question, is the evolution, does the evolution remain globally regular or not? For some evolution equation. So actually this was mainly applied in fluid dynamics, in particular to Euler equations. So suppose we have a function u of, I will explain this in one space dimensions. A function u, a function of time and special variable x, and this is a solution of some evolution equation. And suppose that this evolution equation starts from real analytic initial data. Now we make an analytic continuation of the solution to the complex values of the special coordinates. So rather than x, we have now z, which is a complex variable. Now, this solution is starts from real analytic data, but it typically will have singularities on the complex plane. You'll see an example in a moment. So suppose that the singularity, so we have some singularity on the complex plane, and there will be a singularity which is nearest to the axis, so which has the smallest imaginary part rho. And because we are really interested in real solutions, there will be also a singularity at x minus I rho. So there will be but there will be a strip around their axis, the real axis, free of singularities. Now, this singularity, as the solution evolves, will move on the complex plane. And it might, at some finite time, hit the real axis. If it hits the real axis, it means the solution ceases to be real analytic. So blows up. But if rho, which is sometimes referred to as width of analyticity strip or radius of analyticity, if rho remains bounded away from 0 for all times, the solution remains globally regular. And now the key observation of this method is that we don't really need to study our equation in a complex domain, because the value of rho is encoded in the Fourier coefficients of the real solution. In any textbook, well, good textbook on complex analysis, you will have a result that if you make a Fourier expansion of a function which has a singularity on the complex plane, then the Fourier coefficient will behave for large k like this, so they will fall off exponentially with the rate rho, which is given by the distance to this singularity. There might be some algebraic prefactor which depends on the character of this singularity. So the idea is very simple. Once we have this, so we evolve our equation, and at each instant of time of the evolution, we fit this formula to the solution, and we extract rho, and from this we get rho as a function of time. And if this, well, and there's no question how this rho behaves in time.
Sorry, if you evolved up to some time t, you have the solution at that time, and you'll see if it's regular or singular.
Yes. So this. Yes. So this. That's a good point. So this is. So this method will break down once you have a singularity. So this is a way. So suppose you do this for all times where the solution exists. You get rho as some function of time, and then you try to figure out what is this function. And if you figure out, then you extrapolate. So this method is really based on extrapolations. So let me give you an example which is academic, because this is explicitly solvable. So this is a very simple advection, nonlinear advection equation in one dimension with a quadratic nonlinearity. And let's take a solution which starts with this initial data. So you see these data are real analytic, but they have singularity on the complex plane at plus minus I. This equation can be solved explicitly. This is a solution. And from this you see immediately whether, for example, when x is 0, the denominator goes to 0 at time 1 over alpha epsilon. And then this function diverges. The Fourier transform of this function can be also computed, and it's given by this formula. And of course, in agreement with the general theorem, we see that there is an exponential decay for large, well, actually for all k in this case, and this is our rho. This is the radius of analyticity. And this radius of analyticity goes to 0 as t goes to 1 over alpha epsilon. So we have blow up at time. Well, this example is instructive and related to what I'm going to say in a moment, even in the linear case when alpha is 0. When alpha is 0, well, this is just minus k e to minus t. So in this case, rho decays exponentially in time, but never hits 0. And if you take this solution and compute L2 norms of higher and higher derivatives, which are just like homogeneous Sobolev norms, you find that they behave like exponential function of time with this exponent 2s minus 1. So in particular, for s equals 0, so if you compute the L2 norm of this solution, the L2 norm decays exponentially, which means that the 0 solution is stable in L2 norm. But for any s higher than 1/2, it diverges exponentially. So this example is instructive because it shows that the notion of stability may crucially depend on what norm you use to measure your perturbation. And of course, this is a question, well, which norm is right is a physical question. Okay, so now, so this was just an exposition of this model. I come back now to ADS in 2+1 dimensions. And before I apply this method, I need to remind you spectral properties of small perturbations around ADS. So they satisfy, the small perturbations satisfy the linearized equation with this nice self-adjoint operator. And this can be solved explicitly. The eigen frequencies are even integers, 2, 4, and so on. And these are the eigenfunctions. These are Jacobi polynomials. And using a natural inner product in this space, we can project the solution on the Fourier space. So we define the Fourier coefficients phi k and pk. So this is a projection of the momentum, and this is a projection of the special derivative of the solution. And now, once we have these projections, we can rewrite the total energy. This is the formula for the total energy as a Parseval sum. This is the sum of the energies, Ek, where Ek is defined by this formula as for harmonic oscillator. And this is the energy in the mode of number k. And this is a key object of our study. We are interested how the total energy is distributed among the modes of the linearized spectrum. And this is the result of the numerical computation. So what this plot is showing, this is a logarithm of the energy of the mode k versus the mode number. And this blue curve is energy distribution for initial data. The green curve is the energy distribution for some intermediate time, and the red curve is energy distribution for some late time. And at each moment of time, well, these are asymptotically straight lines, which means that the spectrum decays exponentially. But the number of modes which participate in the evolution increases very rapidly. So initially, our initial data was chosen such that it was concentrated on small wave numbers, and it increases very rapidly. This is for initial data of this form, but this does not depend very much on the initial data, with one exception, which I mentioned. And now, so we now fit, according to this analyticity strip method, this distribution of energy should be well described by this formula, this exponential decay with an algebraic prefactor, and all these coefficients C alpha and rho are functions of time. So we fit this formula for different times, and we get that the radius of analyticity, rho, which is plotted here, this is actually a logarithm of the radius of analyticity as a function of t, behaves as a perfect exponential function. So, with some characteristic decay time, which scales as 1 over epsilon squared. So this, which comes from, well, it's natural from dimensional point of view. So from this, we conjecture, well, assuming, well, this is coming back to your question, for reasons which I will explain in a moment, we can't continue this further, but this is a technical problem. assuming that this trend continues, so assuming that we can extrapolate this, so which means we believe that we already reached the asymptotic regime here, then it means that the solution remain globally regular for all times. However, the radius of analyticity shrinks exponentially to 0, which means that we deal here with what's called weak turbulence. So the energy goes to smaller and smaller scales. But solution remains smooth forever. This type of behavior is probably best known for two-dimensional Euler equation. This has been found many, many years ago. So it's known that for incompressible Euler equation, evolution is globally regular, but exhibits weak turbulence. Well, the technical problem with continuation of this simulation is that, well, this is a typical problem for any simulation of turbulent phenomena. Any simulation is doomed to fail after some time because as energy goes to smaller and smaller scales, you can't resolve these scales using finite differences, even if you refine your grid. So for those of you who know some numerics, this plot shows convergence test. We are using finite difference technique with fourth order scheme. So this is a so-called convergence factor here, which should be equal to 4, which is the degree of this method. And these different curves show how this well, theoretical value 4, the convergence factor deviates from 4 depending on the resolution. So, well, n is the resolution of the grid. Well, of course, with more costly numerical calculations, we could go to higher. Well, we used the highest n we used was 16, which is not very much, which means that we could reach with this method times around 230, but not further. So, okay, and as you showed as you've seen in this example, the fact that the radius of analyticity shrinks exponentially leads to exponential growth of higher Sobolev norms. And what is plotted here is the L2 norm of the second special derivative of the solution for different amplitudes of initial data. And after a short time, they start growing exponentially. So, which means that ADS3 is unstable under small perturbations in the sense of any norm which can capture this turbulent behavior, even though no black hole forms. Maybe I should mention that this turbulent instability, this is related to Gary's questions, this turbulent instability is not active for all perturbations. There exist perturbations for which solutions remain close to ADS. In particular, there exist time periodic solutions. Andrzej Rostworowski will talk about this in the afternoon. This does not mean that solution is well, this does not contradict instability, because stability means that solution remains close to 0 for all perturbations. Right? Okay, so let me finish with some remarks. So this phenomenon of weak turbulence is now a very active field of research in PDE community. And one can study different nonlinear wave equations on bounded domains, on tori and spheres. And not much is known at the moment about this, and this study mainly concentrate on nonlinear Schrödinger equations, which are in this context much simpler than wave equations. What I would like to emphasize that in the case of Einstein equations, this weakly turbulent dynamics can happen only in 2+1 dimensions, because in higher dimensions this transfer of energy to small scales is cut off by black hole formation. But this is not possible in 2+1 dimensions. So I concentrated on small perturbations of ADS, but you can ask what happens for large initial data. In particular, what happens near the threshold for black hole formation. This M=1 is the mass of the lightest BTZ black hole, sometimes called the extremal BTZ black hole. In particular, there is a question whether any solution with mass above 1 will evolve into a black hole. And this is an extremely challenging numerical problem, even in spherical symmetry. And the nature of this threshold, so the transition between global regularity and singularity formation, is an open problem. Franz Pretorius and Matt Choptuik in the paper I mentioned made important progress in this, but we don't have the final the understanding of this problem. And a more general comment is that, so we see here that there is a finite energy threshold for well, in this case, for black hole formation. And this is typical for for wave equations or more generally evolution equations in critical dimensions. That there has been in the recent 10 years or so a lot of work on wave maps in two space dimensions, or Young-Mills equations in 4 space dimensions. These are critical dimensions for these models, where this phenomenon was confirmed. So it means that any initial data which have energy below this threshold exist globally, while to have blow-up formation you need to be above the threshold. And of course, well, this last question is somehow to justify my presence at this workshop, so but I'm not, of course, qualified to answer this. Thank you very much.
Yeah, with regard to this last remark, I'm not a specialist, but I have some friends who do two-dimensional integrable field theoretical systems, be the ansatz. But it's very well established out there that there's no true sense often of real thermalization. Right? There have these non-Gibbsian ensembles at long times, all related to the fact that you have this sort of infinity of conservation laws making it deeply non-ergodic at the end of the day. And I wonder whether there's some direct relation here, whether perhaps these beta ansatz results can be understood by a sort of holographic image of your turbulence.
No, but you are referring now to simulations of fluids, right?
No, I'm referring
2+1
to a
dimensional
massive
fluid.
community of hundreds of people who rely on beta ansatz integrability of two-dimensional field theory. And they look at non-equilibrium, and now it's beta
Two like 1+1.
Yeah. 1+1 dimensional, right? That gives a holographic image of your three-dimensional cavity. I don't know whether anybody has more to say about it.
Well, I'm probably not qualified to answer a question because my understanding of the CFT side is null.
I can just tell you that there are hundreds of people busy with it right now doing exactly this kind of non-equilibrium questions.
Yeah, but those are mostly, but those models would be non-integrable. Yeah, those people would be non-integrable.
Yeah, you see the difference. So I think I think they are not known duals of integrable field theories, right?
Yeah, sorry?
That I think that is what you said. So all this type of model would be non-integrable.
That's right.
Is in my understanding.
Yeah,
right?
yeah.
Also, I'm not an expert. I don't know.
Completely proven fact. Is that a proven fact? Or is that a belief?
I think
There's not clear connection between this picture and the picture that you described in field theory. So it's not obvious that it's
Yeah, no, I'm
applicable
asking
to-
a question, whether there is a connection.
Maybe there is no contradiction.
Yeah, so should I think of this weakly turbulent dynamics as a system remaining in the inertial range for arbitrarily long time in the context of turbulence?
Can you
Can
ask
you
it?
say?
Yeah. So should I think of this weakly turbulent dynamics as a system in analogy with turbulence? Should I think of this as a system remaining in the inertial range for arbitrarily long times? And if so, is there a characteristic exponent that one can extract a la Kolmogorov in this context?
Well, this is a question, of course, how you define weak turbulence, but this is exactly what happens for two-dimensional Euler equations. Well, non-relativistic. I guess we will hear today about relativistic fluid, but for Euler equation, this is exactly this radius of analyticity shrinks exponentially. Actually, there is some mismatch between what is known analytically, because there is some estimate on the decay, and which does not match the numerical simulations. But so this is not this has very little to do with turbulence in the sense of vortex merging or this kind of things. And remember, well, of course, this model would have this actually. Well, part of the last question this is spherical symmetry. So the theory on the boundary depends only on time, so it's trivial. So to make this connection non-trivial, one would have to relax symmetry and to do full 2 plus 1, then the theory on the boundary will be 1 plus 1 dimension.
Is this possible from the gravity point of view to do this theory with less symmetry? Technically.
Yeah, because we are in 2 plus 1 dimensions, and I assume that there is a circular symmetry.
Yeah, but you can relax this.
Yeah, I can relax. So this should be relaxed. And then this would maybe make an interesting 1 plus 1 dimensional model on the boundary.
What would be in this context strong turbulence? What would be strong turbulence in this setup?
Well, usually by strong turbulence, what means that the singularity forms in finite time. So this rho would go to 0 in finite time, in contrast to rho going to 0 in infinite time.
So when this m is between 0 and 1, you could consider exact energy eigenstates in the dual field theory and ask what their dual description would be. And are you implying that the dual description of an exact energy eigenstate would have to have structure on arbitrarily small scales? In other words, it would have to be something like a fractal spacetime or something like that?
I'm not sure I understand your question. So we have no, as I tried to explain, we have no evidence that this conical singularity, are you talking about these conical singularities between 0 and 1?
Yeah, so in the dual field, in the same regime, you could in the dual field theory take an exact energy eigenstate, and you would imagine that its Bullock dual would have a very simple time evolution because it's an exact energy eigenstate in the dual field theory. But you seem to see that if you evolve arbitrary things, that you develop structure at arbitrarily small scale. So would you, if you would want a solution that's dual to an exact energy eigenstate, then necessarily have structure at arbitrarily small scales or not?
But these are still variable. You never settle down. So
No, you don't. But
if you
go right,
But not every solution does that.
Well,
For some periodic ones.
yeah, but they seem to be more not generic, right? Or,
Not even in the
okay, thanks for helping me. Well, I think France and much of it did simulations with a conical singularity at the center, and the conclusion was that it's not much different. So, but this is evolving something which is singular from the very beginning.
Any other questions? In that case, let's thank Dr. Bizet again.